Hey guys, this is the video for 22 and 23. Now we did this in class, but maybe you were taking the bio exam, so I'm going to bring you back through it. It says use the trig ratios and Pythagorean theorem to solve right triangles in applied problems. Okay, so couple things as far as notes we want to review. These formulas, I just used the area at the bottom, which was a space to write. These formulas are provided on the formula sheet, so you don't have to memorize sine, cosine, and tangent. However, I talked about in class that sometimes, and we didn't talk about this back in the chapter, sometimes they instead of using opposite over hypotenuse, sometimes in the application of a problem, it might be more useful to use the reciprocal. So there's this term for the reciprocal of sine, they call it cosecant. Okay, cosecant. And the reciprocal of cosine is actually secant. And secant is a word that we've used before. Remember, a secant line is a line, the through and through, the secant. All right, and then the reciprocal of tangent is cotangent. So these terms do come up on this paper. I don't think it comes up much on a test. You might see it when you get into Algebra 2, but I just wanted to talk about it because it does come up on one of these questions. The other part of this learning goal is the Pythagorean Theorem. So I don't really think of these as formulas, but if you use algebra, you notice that to solve for C, you can take the square root of both sides and C ends up equaling. The hypotenuse equals a squared plus b squared and take the square root. This is a formula I actually use from time to time when I find the perimeter of a shape. And so you don't have to memorize the formula. You just use this formula and use algebra, but some people like to think of them as formulas. So see how a squared is here. If we wanted to get it by itself on one side, we'd have c squared minus b squared and take the square root. And if we wanted to get b by itself on one side, we'd take c squared minus a squared and then take the square root. Okay? So just a few reminders. Awesome. Okay, so thinking of those things, we're going to do question number 1. It said Jack's eyes are 5 feet above the ground, right? And he's standing 400 feet from the base of the building. Okay. Now it says the angle of elevation. So maybe I should make this a little bit shorter. All right, 400. The angle of elevation, so the angle at which they're looking up is 67. So what we see here is we formed a rectangle, and this is going to help us solve the question. It says, how tall is the building? So we know that opposite sides of a rectangle are congruent, so that would also be 400, and that would be 5 on the left and the right. So whatever the height of the building would be, if we solve for x, we want to make sure that we add 5 before we put our final answer. Okay? All right. Now I'm ready to do my trig. I have a right triangle, and I'm going to label my sides. So here we go. We got our reference angle. I'm going to label this opposite. Opposite the box is the hypotenuse, and this would be the adjacent side. Okay? So it looks like I have information for opposite and adjacent. So that would be tangent. The tangent of 67 is opposite over adjacent. So the tangent of 67 is x over 400. Now using the Lynch swap, we're going to move the 400 up here with the tangent of 67, right? And you could also think of this as just multiplying both sides by 400. And canceling. It's the same thing, really. The Lynch swap is just a shortcut. And so now we're back to our calculator. So it's 400 times the tangent of 67. So the tangent of 67 is 2.355. So I'm going to take 400 times that amount. Right? So times 4. Hold on. The tangent of 67 times 400. 942.3. 942.3. Now remember, I promised we're going to add 5 here, so I get 947 if I rounded to the nearest foot, and that's my answer. Cool. Next question. Garrett makes a ramp for his skateboard. It says the length of the ramp part is 2, and one of the legs is 1. Okay. So which trig ratio would describe the relationship? So either I can pick this angle, or I can pick, I'll call this angle A, right? Or I could call this angle B. So here, if I pick the sine of A would be opposite 1 over hypotenuse 2. Or I could pick B here, right? Angle B, this would be opposite. So this would be adjacent to B. This is the side adjacent to angle B, and this is still our hypotenuse. So that would be the cosine of B is 1/2. So notice we already know this, that if those two numbers are complements, we talked about this before, then they should be equal to each other. So we're noticing that the sine of A and the cosine of B are the same number, 1/2. So what is that number? You can use trig, or you can just kind of play around with your choices and a calculator. So either way. So if I use trig, I'll take the inverse sine of both sides. So I'll take the inverse sine of both sides. And you could do the same thing here, but I'm going to take the inverse cosine of both sides. And what I end up getting if I rewrite this is the inverse sine of the sine of A is just this A, or the measure of angle A, right? And the inverse sine of 1/2, or 0.5, we'll find out. And so what is the measure of angle B? Well, it's the inverse sine of, or excuse me, the inverse cosine of 1/2. So let's see what that is in our calculator. So I'm going to have to hit that second button, but the inverse sine of 1/2 is 0.5, and then second sine second sine 30. Nice, right? So this would have to be 30. And what's the inverse? 0.5. Second cosine 60. So I kind of already knew that using special right triangles, but trig works. So how did I know that? Well, I kind of know from an equilateral triangle. If all these sides were 2 and you cut them in half, that'd be 60. That's 60. You cut 60 in half, you get 30. That ends up being 1. So that's how I knew that arrangement of 1/2. Now, this is actually different than we did in class. In class, I just used a calculator. So you can find here, the sine of 30 is 0.5. The cosine of 60, 0.5. So this is 0.5 in a calculator. This is 0.5 in a calculator. The tangent of 45 in a calculator is 1. I think this one is 0.707, so that's not 1/2. This one is also 0.707. Let me see what the tangent of 30 is. So the tangent of 30 is 0.577. So the only ones that are the ratio 1/2 are these cosine of 30, or sine of 30 and cosine 60. Cool. Okay, Michaela's shooting a paintball gun from point G to her target. What is her angle? All right, so I'm going to put this, call that X, right? And we'll label that opposite. Opposite the box is hypotenuse, and this would be our adjacent side. So like one of the previous questions, we're going to use the tangent of X. And the tangent function is opposite over adjacent. So the tangent of X is 28.2 over 45.8. So now to find the missing angle, we need that green button, that missing angle button on our calculator. So we have to find the inverse tangent of this fraction, 28.2 divided by 45.8. 28.2. All right, and we get 0.6157. 0.6157. Now I'm going to do that inverse tangent. So I'm going to hit second tangent. I get 31.6. So the measure of angle X is 31.6 degrees. And I look in the picture and I say, oh, that looks about right. I think that's a pretty good looking answer. All right. Question 4. This one's pretty similar to our first question with Jack. The angle of elevation is from a viewer to the top of a building is 50. And the viewer is 80 feet away. And the person's 5.5 feet tall. So kind of the same type of problem. I'm going to solve for the height. I'm going to solve for X and then add 5.5 before I come to my final answer. Okay, so I see I have a right triangle, and I'm going to label the sides in relation to this reference angle. This would be opposite. I don't have anything for the hypotenuse, and the adjacent is 80. So I need the tangent function. The tangent of 50 is opposite over adjacent. Cool. Now I'm going to multiply 80 on both sides, or the Lynch swap, whatever works for you. And there's my answer. So tangent of 50 times 80. Tangent of 50 times 80. 95.34. So X is 95.34. Now, that looks pretty good, right? I'm looking for a number bigger than 80. I got my wish. And I'm going to add 5.5 to get my final answer. So, and I'm going to round to the nearest tenth. So that would be, just go back to my calculator, plus 5.5. We get 100.8. 100.8 feet. Well done. Ooh, another trig one. Now it's saying the 30-foot long escalator, so that's the surface of the escalator, which is the closest height. So it actually is admitting these are not exact, but what would be the closest? So we're going to call that X, and let's set this up. So here's our reference angle. This would be opposite the reference angle. This is opposite the box, and this is our adjacent side. So we have 30 to plug in for the hypotenuse and X to plug in for the adjacent. So I'm going to pick cosine. The cosine of 41 is adjacent over hypotenuse. So the cosine of 41 is X over 30. So moving that 30 on up, we can find our answer by taking the cosine of 41 times 30. So the cosine of 41 times 30. I get 22.6. And this is pretty close. So that's our answer. It says it's just not going to be exact answer. We pick the one that's closest. Item 6, we get a hamster rolling down a slide, and we've got a reference angle. So it says, what is the distance the hamster had to travel? So we're going to make X the distance they want me to solve for. And this would be the hypotenuse. So I need sine. The sine of 40 is opposite over hypotenuse. So the sine of 40 is the opposite side is 15. And the hypotenuse is X. And now you notice a lot of people don't like X on the bottom, right? So this is the true Lynch swap. Notice I can move the X here and move the sine of 40 down below. Pretty handy. But none of my answers are here. So if I look at this, remember what I said before in the beginning, this is the sine of 40 times 15. And I said the reciprocal of sine is cosecant. That's abbreviated CSC, cosecant of 40 times 15. That answer is right there. So the cosecant of 40 happens to be the reciprocal of sine. And a computer would possibly solve this with cosecant because it would cut down on the number of steps it needed to do to solve the problem. That's what a computer does. It reduces the number of steps it has to take to preserve processing time. Okay, last one on this page. A diagram shows a ramp containing a platform, right? And it says, what is the angle of elevation round to the nearest degree? So I'm solving here for this angle, right? And so let's label the sides opposite, and opposite the box, the hypotenuse. So we have sine again, right? The sine of our angle x is opposite over hypotenuse. So now I have to find the inverse sine of the sine of x so that I can get x by itself on one side. And on this side, I'm finding the inverse sine of this. All right, so let's use the calculator. 4.5 divide by 1175. 4.5 divide by 1175. And I'm going to go second, solve for the missing angle button, sine, 22.5. So it said round to the nearest degree. So 22.5 would round up to 23 degrees. And I want to make sure that makes sense. I think that does. Yeah. 4.5 is a lot smaller than that. So I'm looking for a pretty small angle. So remember on our calculator, I need to first hit the second button, which happens to be green, and then I hit the sine button in order to get this trig function right there. And it's the green button, so I'll make it green just to remind you. All right, the other page we did was proving all circles are similar. So I think that that's actually pretty intuitive. Most students I have are like, yeah, this is similar because I can move this over and then shrink it. So it's pretty obvious that all circles in the universe would be similar. So if I look at this question, mapping O and pulling this point over here and dropping it there on top would be good, but then I'd need to shrink it, and I don't see any dilation. The second choice says take this one, drag it over here, lay that on top, which that would work just nice, but you need to dilate it, right? You'd need to blow it up. So I'm going to choose neither because both need to either enlarge or reduce, blow up or shrink using dilation. So in order to prove that two circles are similar, that are different in size, you need both a translation and a dilation. You've got to have both. Okay, let's look at question number 1 now, because I've kind of explained what similar triangles are. What would be the ratio of these lengths? So notice these arc lengths, S equals pi r. What's the ratio of these arc lengths? Well, this arc length is theta, which is the angle here, and the radius, which is a. So the big circle has an arc length of pi times a, and the little one has the same formula. The smaller one has an arc length, same angle, theta, right, times b. Now, would these make the same ratios? So if I put them in a ratio, the big one over the small one, I get theta A over theta B. Notice this would cancel. They'd make the same ratios as the radius of the big one and the radius of the smaller one, right? So this proves that both their arc lengths and their radii, both their radiuses, make the same ratio. And that's how I know that they are similar. Okay, so let's think about this. In a way, circles don't have sides, right? But so similar by definition in a polygon would be the angles are the same and the sides make the same ratios. Here I have the circumference or the arc lengths make the same ratio. So in the same way, it's the same ratios. So which statement would be true for any two circles? So let's give an example. Let's say our circle has a radius of 10, and I have another circle quite a bit smaller with a radius of 5. What would make the same ratio of the radii? So the radii would be 10 over 5, right? The radius of the big one over the radius of the small one. Which ratio would that equal? Well, the circumference of this would be 2 pi r, so 2 times pi times 10, or 20 pi. And the circumference of this one would be 2 pi r, or 2 times pi times 5, or 10 pi. So the circumference of the big one over the circumference of the small one would be 20 pi over 10 pi. So notice both of these would reduce to 2. So they have the same ratio. Would the areas have the same ratio? Well, let's see. This would be, the area of this circle is pi times 10 times 10, or 100 pi. And this circle on the right would be pi times 5, or 25 pi. Well, if I took the area of the big one over the area of the small one, 100 pi over 25 pi is actually 4. And that's not equal to the radius of the, not equal to the ratio of the radii. It's also not equal to the ratio of the diameters. Here, my diameter would be 20, and here my diameter would be 10. So I do get the same thing. I get the same, this would be the ratio, the radius, or the diameter. So what's wrong here is the fact that they're talking about areas. We notice the area is not a match. So question 4, which statement would explain why all circles are similar? As we said, the ratio of the circumference is the same as its diameter. Yes, nice work, guys.